Log on, tune in, find out. Another good idea from Cambridge.
Underlying Donaldson-Thomas.
Okay, thank you very much for the invitation. So, so let me start by giving a brief outline of my talk. So first, I should explain what calculi are, just the definitions and a few basic examples. Then second, I want to motivate this. So this is the motivation I want to talk about is categorification. Of Lagrangian intersection numbers and Donaldson-Thomas invariance. And then the third part is actually about the results, or a result which is joint work with Ezra Getzler. I want to construct. Well, it's just half a calculus, and this is also work in progress, and so. So this is for moduli of sheaves on a Calabi-Yau threefold. So, so this terminology is due to Chamarkin and Segan. This calculus. So, what is a calculus? So, so a calculus. The following data. So there's two main parts. So first of all, there's A. So this is A is a unital graded commutative algebra. So wedge is this graded commutative product with a bracket operation. This is this bracket. Which is of degree +1. It's the bracket is a derivation with respect to this product in each of its arguments. It satisfies graded Jacobi. So derivation and graded Jacobi. So it's like a Poisson algebra, except for the bracket is of degree +1, so this kind of thing is called a Gerstenhaber algebra. The second half of the calculus is module over A. So by contraction, this contraction symbol denotes the module structure of A on omega. So this is a graded A module. With a differential D, which also of degree +1. So it satisfies D squared equals 0. And there's a compatibility relation such that I'm going to write down this formula. So a differential applied to A, which B on omega plus -1 to the that's the degree of A plus the degree of B. A wedge B contracted with d omega plus minus 1 to the A bracket of A and B contracted on omega is equal to minus 1 to the A contracted with d omega plus minus 1 to the A, B plus B. Let me give you the main example, which you're all familiar with. So M is a complex manifold. Let's say of dimension n, which can be infinite in some cases. So in that case, I could say this is a Hilbert space. I mean, manifold model on Hilbert spaces. A is the exterior algebra on the tangent bundle. So this is the holomorphic polyvector fields. So this is all in negative degrees. So the tangent bundle is in degree minus 1. So this is the wedge product of polyvector fields, and the bracket is the Lie-Skelton bracket. Which is the unique extension of the Lie bracket to this whole thing, satisfying, making it a Gersten-Haber algebra. And omega is, of course, a module of differentials. So this is in positive degrees. And with the exterior differentiation. So this is a sheaf of calculi. Okay, next definition. A differential calculus. Well, so this is a calculus which has, in addition, extra differentials flying around. So x has, in addition, so let's call this Q. So a differential on A of degree plus 1, which is a derivation with respect to both the products and I don't know why I call this S, but another differential on omega. Which makes this a differential graded module over the differential graded algebra. So and commutes with D. So just extra differentials on the whole thing, which are compatible in the natural way with all the structure. And there's a, trivial lemma that if you have a differential calculus, you can pass through the cohomology with respect to these extra differentials, and then you get a calculus. So if I have a differential calculus, this is the direct sum of all the cohomology spaces. So of A with respect to Q and of omega with respect to S with the calculus. And so there's also a easy example of that. In the context. So in that example up there, as above, omega, a closed one form on M. So this is going to define these two extra differentials. So Q is the contraction against omega. So I can contract polyvector fields with omega, and each time I contract with omega, the degree goes up by 1. Okay, and then S is multiplication by omega. So this is multiplication as wedge product of differential forms, which is not part of the structure of the calculus, but I can still use it to define this differential. And okay, and because the form is closed, therefore contraction with omega actually commutes with the Lie bracket, and the multiplication with omega commutes with D. That's why I need closed. So this defines a sheaf of differential calculi on M, and then if we pass to cohomology, we get a sheaf of calculi on X, which is the scheme theoretic zero locus of omega. So it's defined by this fiber product. So here's the zero section of M into its cotangent bundle. Here, the section omega, the closed one form, also defines a map from M into omega, which I'll denote as the graph of omega, and X is the fiber product. So I want to emphasize that this is a symplectic manifold, and these two are Lagrangian submanifolds. I mean, because omega is closed, therefore this embedding defines a Lagrangian submanifold, and so this is a sheaf of calculon on a Lagrangian intersection. And in this case, so these cohomology sheaves HI of the polyvector fields on the ambient with respect to contraction with omega. So these I'm going to call OXI. These are higher structure sheaves. Which is not hard to check. These are actually the core sheaves. Oh, damn this thing. Oh, eventually this. Of the structure sheaf of these two structure sheaves over that one. Okay, so these have a bracket. And that's the main reason why these things have a bracket is because it's a Lagrangian intersection. I mean, these sorry, I should have mentioned, of course, these are supported on X. And the zeroth one is a structure sheaf of X, and the higher ones are coherent sheaves on X, and then I have this bracket. I'm going to use this epsilon notation for the cohomology of that thing with respect to omega. So these you can check are the X sheaves of this intersection. So these have an action of the higher structure sheaves, and they have this differential D, which, and we have this formula. So I have a calculus. And this, well, because this is what I call the virtual calculus. Of the Lagrangian intersection X. Maybe I'll just say this, that in this example, if we are on a finite dimensional complex manifold, well, so let's make it so if n is less than infinity, then actually because if you take any non-vanishing, so just I guess I'm explaining this. Right, you have Tm. You contract with omega, and this defines the structure sheaf of X, this co-kernel. And if you look at the highest exterior power of M, and you multiply with omega, right, that co-kernel is by definition the highest one of these modules. And so you see that if you choose a lower vanishing top degree form, this identifies with this and that identifies with that. So this is locally free. And so if you choose such a trivialization, then you can identify the epsilons with the O's, and then you can transport the D onto the O by transport of structure, and then so identifying these two. So if you can, then that gives D on O, making D a potential for the bracket. That means that you have the following formula. Just set omega equals to 1 in that formula, and you get this formula here. So D is then not a derivation with respect to the wedge product, but the failure of it to be 1 is actually exactly measured by the bracket. So that's any such D is called a potential for the bracket, and then this makes this this O Bartalian-Wilkowiski algebra. But I mean, I emphasize that this only works after choosing such a local trivialization, and you need to talk about this higher x0 power you need to be in the finite dimensional case. Okay. Let me just give quickly one example. Suppose that x is smooth in this case. I mean, it could happen that the intersection is smooth. I mean, the expected dimension of the intersection is 0, of course, but but let me not assume that it's the expected dimension, just that it's smooth. Okay. Then you can check, it's not easy at all, that sorry, not difficult at all, that that these higher structure sheaves are just the standard polyvector field on X itself. And if in the finite dimensional case and C is the codimension of X and M, then this epsilon guys are just up to shift the standard standard ones. This is not hard to check. So if the Lagrange intersection happens to be smooth, then this virtual calculus is just the standard calculus, except for this module part of the calculus has to be shifted. So you essentially get the standard calculus back. So in that case, you don't get anything new, but in the general case, you do get something more interesting. Another thing is okay, so if this thing is just the standard calculus, so then we see that the cohomology of this epsilon with respect to D, if that's just a standard de Rham complex on a smooth manifold, well, that is a resolution of the constant sheaf C. Well, now it's a shift because of this shift here. So this is a local system, so a shifted local system. And if the intersection happens to be compact, then the intersection number is well defined. So let me denote the intersection number like this. So that's the top Chern class, the Euler class of the obstruction bundle. Sorry, the excess bundle of the intersection, which is the restriction of omega m to x divided by the normal bundle. Which you can check is the cotangent bundle of x. So this is up to sine, which is the dimension of x. The Euler class of the tangent bundle, and this is by Gauss-Bonnet minus 1 to the dimension x of the topological Euler characteristic of x, which is the alternating sum of the dimensions of the cohomology groups, of course, I can put this sign in there by shifting this complex like that. And then I can write this in terms of this epsilon. So this is epsilon complex shifted by the dimension of the ambient n. So the intersection number is equal to this of the sign, the topological Euler characteristic, which is the Euler characteristic of this de Rham complex shifted by n. And I'll explain in what way this generalizes to the general case. But first I want to mention that so there's a theorem of Kapranov in '89 which says that these cohomology, so the cohomology sheaves of cohomology sheaves, so the cohomology of this virtual de Rham complex are constructible. So in this case, the smooth case, they were just a shifted local system. In general case, they can be constructible sheaves. In particular, you get that the hypercohomology groups are finite dimensional. So these are the virtual de Rham cohomology groups of the Lagrangian intersection. Right, so even when X is not compact, the virtual de Rham cohomology groups are finite. You can define, therefore, a constructible function. Well, because these things are constructible, these sheaves you can compute fiber-wise Euler characteristic, which you can write like this as the dimension of the hypercohomology with supports at the point P. So this is a constructible function. And if you want to compute just the Euler characteristic, so the alternating sum of the dimensions of the virtual de Rham cohomology groups of these guys, then you can just compute the Euler characteristic of X weighted by that constructible function. So this is this finiteness theorem. Okay, now I have to talk about something different for a moment. Oh, I should have not erased that picture of always my intersection. So Lagrangian intersection numbers. So there's a theorem. So consider the following function. So this is mu. And actually I want to now assume that choose a antiderivative of omega, which is closed, so locally you can find such a thing. And calculate this number. So you take the Miller fiber, so here's M, well, there's M, there's F going down to C, here's the critical set X, and so you take the Milner fiber, which is the, you intersect a nearby fiber with a small ball around the point P. So that's the Milner fiber of F at the point P. Compute its topological Euler characteristic, subtract 1 and change the sign. Okay, then this is a constructible function, meaning constant on a stratification, and if X, the critical set of F, is compact, then the Lagrangian intersection number, well, this is now dF, is the weighted Euler characteristic of the intersection weighted by this function. So this is the Milner number. I call this function the Milner number. So weighted by the Milner number. Let me explain why is that true. This is well, there's a old theorem by Le and Nephoud that well, so the characteristic cycle, let's say phi f is the perverse sheaf of vanishing cycles for f, and that has a characteristic cycle, and that's what I denote by this. That is the same thing as the normal cone. The normal cone of this X inside M. Therefore, this is normal cone. Okay, so therefore this Lagrangian intersection number assuming that this intersection is compact, well, it's defined in terms of the normal cone, so it's in terms of this characteristic cycle. Actually, this is probably and then by the so-called microlocal index theorem, which is due essentially to Kashiwara, McPherson. This is then because of this essentially that the fact that corresponding to this characteristic cycle is this constructible function, which is again the fiberwise Euler characteristic of this complex, which happens to be this one. So in the general case, we always know that this Lagrangian intersection number is actually an Euler characteristic with weights given by the Milnor number. Now up there I talked about some other constructible function which is called nu, and well, I only did this because there's a conjecture that these two functions are equal. So this is a conjecture, and this is also, well, I think it's due to Kapranov, this conjecture. Well, at least in the K group of constructible complexes, we have that this virtual de Rham complex is equal to the vanishing cycles complex. So classes are equal. Maybe there's a sign somewhere. So this is the perverse sheaf of vanishing cycles. In particular, actually, this is equivalent to this, that nu is equal to mu. These two constructible functions are equal. So, so these are equal. So therefore, right, this should be the generalization of this fact. For the smooth case, it was easy to see that this was just a de Rham complex, which was a resolution of the constant sheaf C. Now the constant sheaf has been replaced by the vanishing cycles, and the de Rham complex has been replaced by this virtual de Rham complex. So unfortunately, in general, it's just a conjecture. So if the conjecture is true, then and we are in the compact case, then the Lagrange intersection number, which is equal to, this is what we know by the conjecture, this would be equal to this one, which is the sum minus 1 to the I dimension and then the Lagrange intersection number isn't just a weighted Euler characteristic, which is some kind of motivical thing, but it's actually an alternating sum of dimensions of cohomology groups. And so then this is, if this kind of equality holds, then I have categorified these intersection numbers, and the categorification is this cohomology theory. So this is well, so of course you could say there, I could replace, instead of writing this virtual de Rham complex, I could write the perverse sheaf of vanishing cycles, and then I would actually have an equality, not just a conjectural equality. And then I would also have a categorification, because I can write this as the alternating sum of the dimension of the cohomology groups of vanishing cycles. But so conjecturally, both of these, well, it's not even clear that the conjecture implies that the cohomology groups will be the same, but the numbers will be the same. So it's like, so it's like, you know, Euler characteristic is either you can use Betti cohomology or de Rham cohomology, the same thing in the virtual case. And this is the de Rham approach. So okay, so now let me talk about moduli of sheaves on a Calabi 3. So now y from now on is a smooth projective Calabi of dimension 3. For example, the quintic in P4, and we want to assume for technical reasons that the first cohomology of y with O vanishes. Let's say E as a Schur object in the derived category of y. So the derived category is the derived category of complexes which bounded coherent cohomology. Okay, and the Schur object in there, well, E. So what does the Schur condition mean? That it talks about the extensions of E with itself, and but I'm always going to use traceless x's, so that's denoted by the 0 down here. And this has to vanish unless I is equal to 1 or 2. So, for example, a simple bundle. And yeah, okay. So first talk about the local situation. So let X be a moduli space with a point in X, and this is the point corresponding to my given Schur object. So, and it's some kind of modular space of derived category objects or modular space of simple bundles. Okay. With trivialized determinant, and this is the condition we need to assure that there is no infinitesimal automorphisms, and so this, I can think of this as a space. Now you can use Kuranishi theory. Well, any scheme you can locally embed into the tangent space at that point. So but Kuranishi does a little better. So embed X only in a small neighborhood around P, so near P, into the tangent space to X at the point P, which is this extension group. As so there's an analytic map called F that goes from the tangent space to the obstruction space. Well, and that's the obstruction space, so this is the tangent space. And so there's the scheme theoretic zero locus of this, so this is holomorphic. It's only defined in the neighborhood of the origin. Right, so it's not all of X, it's just part of X, but anyway. Okay, now we use Serre duality, which doesn't involve the canonical bundle is trivial, so when I write down Serre duality, it doesn't mess up the formulas. This is directly the dual of that. So Serre duality says that x2 is x1 dual. So this is actually a holomorphic map from this vector space to the dual space. Dual. And so it's a holomorphic one form. So F is a holomorphic one form on x1 EE. And well, you have to work a little bit to show that it's a closed one form. But it is closed. And so we're in this so at least locally, so locally our modular space is such a zero locus of a closed one form. So therefore we have a differential calculus on this linear space x1 EE, and by passing to cohomology, a calculus on x near P. In particular, well, if you want, in particular, you can define this constructible function nu, this, so this is maybe the punctual de Rham dt invariant. Of the derived category object. And of course, you can, because it's closed, you can locally find an antiderivative, and this is that thing would be called a holomorphic Chern-Simons function, and conjectural, this guy is equal to the Milnor number of that holomorphic Chern-Simons function by that Kapranov's conjecture. Okay. Now, so locally we have everything, but globally, that's the question about global. So well. So it's hopeless to try to glue these local calculi together. I mean, even they're supported by these X spaces, and even the dimension of these X spaces, they keep changing as you move around in X, so it's not at all clear how you would try to glue those together. And even if you could, I mean, the fact that this bracket and the differential are not linear over functions makes it really hard to construct them locally. Anyway, so we don't try to do anything like that. So this I should say here now is the part which is, well, okay, we write X globally as zero scheme, or analytic space, I should say, of a closed holomorphic one form on Hilbert space manifold. Right, so we have to go to infinite dimensions for that. And so let me just write down the theorem. So suppose X is a compact moduli space of sheaves on Y. Then there exists a global sheaf of Gerstenhaber algebras so there's the higher structure sheaves of X with a wedge product and a bracket. Which reproduces locally the ones coming from the Kuranishi story. So because of that, we can deduce that in particular this is a coherent sheaf of algebras graded algebras and locally this bracket admits a potential because that's true for these finite dimensional stories that I explained before. So as I said, this is only half of the calculus, only the Gerstenhaber algebra part, so it's because of the infinite dimensional. So I don't know how to do the other part of the calculus yet. So of course that other half of the calculus is the one that we really need to categorify, but well, this is already quite interesting, I think. Okay, so I just want to say a few words about the proof. Well, 1, 2, well, okay, let me just say a few words. So first of all, restrict to bundles. There's a trick explained in the Joyce Song paper, how to replace, you can replace sheaves by their third syzygies, basically, and that way sheaves become bundles, and so you only have to talk about bundles, not sheaves. So that is a big simplification, because then we use gauge theory. So you start with a fixed E as a fixed holomorphic vector bundle on Y, and then you look at all other holomorphic structures that you can find on the underlying C infinity bundle. So so the main thing you introduce is this L. So this is so this is the sheaf of traceless endomorphisms of E, or the bundle actually, and these are forms of type 0 something, so C infinity forms of type 0 something with values in that bundle. So this has a differential which comes, so this has a differential coming from the d-bar operator, which gives the fixed holomorphic structure that we started with, and it has a bracket. But actually, it has an associative product coming from the composing endomorphisms and multiplying forms, which induces then by anti-symmetrization of brackets. So this is a differential graded Lie algebra. Actually, it's only there's only 4 graded pieces to it, and then you write down a gauge group. So those are all the you put a 0 here, and you require the determinant to be 1. So determinant 1. C infinity automorphisms of E, and then you write down the curvature map. So F, which goes from L1 to L2, and then the 0 locus of F divided by the gauge group is contained in L1 divided by the gauge group. And so this is going to be essentially our modular space X, and this is a smooth manifold in which X is contained. We will pass to the simple locus where G acts without stabilizers, so that this really is smooth, this quotient in there too. But I mean, since all the objects are going to be Schur objects, this is okay. And so so this is the rough story. Well, and then, I mean, okay, then you use, let me write down this Serre duality pairing. It's not even written here. Where is it? Kappa of AB is the integral over y of the trace. So omega is the Calabi-Yau form, the volume form, the holomorphic volume form. If I and if A and B have complementary degrees, for example 1 and 2, then this product will have degree 3. So this is of type 0, 3. That's of type 3, 0. Altogether, get a form of type 3, 3, which I can integrate over y. This sets up a pairing between L1 and L2 and L0 and L3. So in particular, we get L1 to L. Well, here's the curvature map F to L2, and L2 goes to L1 dual via this kappa, and there's like kappa of F. And of course, you want to use this thing which induces Serre duality to turn this curvature map into a map from L1 to L1 dual, so into a 1 form, which then you want to prove it's closed. And so then, right, so this will be closed. And then, and then essentially, so what will happen is that X, which is the 0 locus of F, because of this diagram, where all its formal consequence is contained in the 0 locus of this closed 1 form. And then Then we have written X as a Lagrangian intersection globally, okay, in infinite dimensions, but that's good enough. But I have to point out that there's some major problems with all this because, I mean, I could talk for another hour on this, but I won't. So just, so there are some serious problems here that have to be overcome. So first of all, to do geometry, you know, you really have to talk about Hilbert spaces here. So you have to pass the completions. So you have to complete L, right? So that you get a Hilbert space differential graded Lie algebra. And so you're going to have to introduce some Sobolev norms. And then there's various requirements. So the requirement that you know, you want this curvature map to be bounded. So you have to have that this differential has to be bounded and the Lie bracket has to be bounded. And that puts certain conditions on what kind of Sobolev norms you want to take. And then also to make the Kuranishi stuff work, you get more conditions on the Sobolev norms. In the end, you see that these requirements will, well, so we get strong restrictions. I mean, on the Sobolev indices, which then will force that this map here is not an isomorphism. This L2 is not isomorphic to L1 dual. So really, if you're talking about infinite dimensional analytic spaces, this is just an inclusion. This is not an equality, which is a serious problem. Which means that yeah, everything falls apart. You know, it's not. If X is a zero locus of F, not of this closed one form. So that means you have to work harder and you have to modify this Serre duality pairing. Modify this to also include higher derivatives like in the Sobolev norm. So modify this to include higher derivatives. Okay, then you're all messed up because then this isn't cyclic anymore. So more, you know, it seems like you keep, you know, biting yourself in your own tail and never get anywhere. But in the end, it does work. And so I just want to indicate some of the problems that occur here. It's not completely trivial, but it does work.